So, during the last lecture, when I was discussing the blast furnace material and enthalpy balance, I had come to a point where I have written on the blackboard three different equations. One, the overall oxygen balance equation; the second, the Oostite reduction zone oxygen balance equation; and the third, the Oostite reduction zone or the bottom segment enthalpy balance equations. And as I had indicated during my first lecture, that we would like to have a fully predictive model. So, therefore, for the three unknowns that we desire to seek in this exercise, the top gas composition or the O/C ratio in the carbonaceous portion, the active carbon rate or the coke rate of the furnace, as well as the blast rate, and they could be expressed in terms of three different. I write it overall oxygen balance equation. Then we have Oostite reduction zone oxygen balance equation, and we have Oostite reduction zone or bottom segment enthalpy balance equation. And these equations, in terms of our standard terminologies that I have introduced for an idealized operation where I use hematite ore, and this is where for the idealized operation I have shown, or I have this term we know what it is. It has three different components: demand WRZ or the bottom segment Oostite reduction zone. That is, you have to provide the heat of formation to break the bond. Okay. Then you have to take that resultant iron at 1200 degree to 1800 degree centigrade. There is a second component, and the third component is that in that iron which has thus been liquefied, you have to put in 4.3% carbon, which was initially entering the system at 1200. Okay. So, there are three different segments in this DWRZ, and for the idealized blast furnace operation, this 330,000 kilojoules per kg mole of Fe. So, this form our fully predictive models. Okay. And also I have represented, and if you remember that where from this 198,000 term has come, let me write it down for you once again so that we can recapitulate, because that is going to be useful for us. So, the 198,000 has come from EBNOB, that is the first term, and we have NAC, and then we have here 2 minus O/C gas Oostite reduction zone into heat of formation of carbon monoxide at 1200 and plus O/C minus 1 into heat of formation of carbon dioxide at 1200 Kelvin. That is from where, okay, we have substituted the values of heat of formation of CO, which we have taken to be 113 kilojoules per mole of carbon, and CO2 is 395, so 1000 kilojoules per mole of. That is when you substitute the value with a negative sign here, of course, because the heat of formation is going to be taken as negative values. Okay. These are the magnitudes that I have written, and then you get, when you substitute gas Oostite reduction zone, which is your It looks more elegant if I put a second bracket here, if I put a second bracket here, and if I put a second bracket here. Okay? And we know that this value is 1.c. O by c is 1.3. So, if you substitute the value, so this is known, these values, so that means that an explicit numerical value will result, and that numerical value has been shown to be is equal to 198,000. Okay? Now, I have also represented a combined enthalpy and bottom segment oxygen balance equation, and that is possible once you substitute that this EB, that means the replacement of the NOB term, which is equal to 1.3 NaC minus 1.06. Okay? So, that is what is the NOB term according to the bottom segment oxygen balance equation. So, if you substitute this, the resultant equation becomes the combined oxygen balance, and this is going to be, as I have indicated, so EB 1.3. So, therefore, I can take the NaC common, and then I can write it is 1.3 EB plus 198,000 and then minus 1.06 again EB. And this is the combined and bottom segment oxygen and enthalpy balance equation. Because I had indicated during my last lecture that we have represented these two equations in a O by C plot, if you remember, O by Fe on this, and this is O by C. So, that is a plot that we have generated and I have drawn with regard to this question, two equations, and I have also indicated that the W essentially represents a point which is O by C is equal to 1.3, and this is where for an idealized operation this point essentially is 1.5, this point is 0 comma minus NOB. That is what is this particular point, and this is our 1 and this is our 2. So, this represents the O by C gas that we know from. So, I want to now visualize these results, the bottom segment enthalpy balance equation that I have derived in terms of the plot O by Fe plot, and we must realize that it is difficult to translate this or superimpose this data onto this, because what happens is these are all the units are O by Fe, the unit of this term we are plotting here, moles of oxygen per mole of Fe versus moles of oxygen per mole of carbon, that is the plot. But here the terms are actually kilojoules per mole. So, we really cannot visualize this result in terms of the plot that we have generated, but we are interested to do that, and that is why I have derived the combined oxygen and material balance equation, which can now be translated in terms of various terms, where we will get some terms in terms of dimensions of O by Fe and some terms in dimension of O by C. Now, let us see particularly this term. Okay? If you open up this term, then what happens is you have, so I will write minus, okay, and we have NaC. Okay? So, if you multiply 2 times heat of formation, and then we can combine the terms which are numerical and combine the terms which are having O by C. So, the first term I can write NaC, okay, and then we can have here, for example, HF 2 times HF heat of formation of CO 1200 minus and this is I have taken minus here. So, I am opening up the bracket. So we have this, and then we have minus and minus. So this is going to be HF, heat of formation of carbon dioxide at 1200. That's going to be one particular term. The other term is going to be, if you take the NaC common, and NaC again make it negative, and then we take also the O by C. We are not substituting it, we will substitute O by C, gaseous state reduction zone, later on, gaseous state reduction zone. And then what we are going to see here is nothing but O by C. We are going to see heat of formation of carbon monoxide minus heat of formation of carbon dioxide at 1200. That is the value that we are going to see. And if you remember that this value is going to be now 2 into minus 2 into 113,000. This value is going to be minus 385, 95,000. I have written it here somewhere. I think maybe I have erased it, 395,000 kilojoules. These are all kilojoules per mole. Okay? And therefore, when I do this, then what I am going to get here is, this is a positive sign. So, the net term will come out to be a positive quantity here. Okay? On the other hand, if we do this here, 113,000 minus and minus this, so 395,000, and we open up the bracket. So, what we are going to get here is this term also we are going to get as a positive term. Okay? So, 113,000 minus, and then this is plus, minus and minus will become plus. So, we will get 282,000. Okay? And if you do this, the net result here is that we will get a term called 282,000, and if you do this 2 into 116, so we are going to get, say, a term called 169,000. That is the term that we are going to get. So, now we have, there are some terms common with NaC. So, we can restructure this equation and we can write, for example, dWRZ. If you remember, the last term is going to be the combined balance equation is minus 1.06. So, I will bring this 1.06 here, 1.06. So, and on this side, therefore, I will have all terms associated with NaC, because this term is also associated with NaC, this term is also associated with NaC, and therefore, what I am going to get here is NaC. If we just manipulate it, and this is going to be 1.3 minus 169,000 and then 282,000 plus EB. That is a simple arithmetic exercise. Okay? I have shown that where from 169,000 has come, where from 282,000 has come, and that 282,000 term is now here. So, that is. So, this can be, with the values substituted there, we should be able to get the equation from here. We can get the equation straight away into this particular form, because this term 282,000 term can be, because this is also associated with 1.3 EB. So, this term is also associated with 1.3 into 2, So, 1.3 term is here, 1.3 term is here. So, the moment you take it common, then what happens is 282,000 gets clubbed with enthalpy of the blast, and then you can divide it and transpose and then get to this particular form. So, from here getting to this particular form is a class 10 exercise. Let me not spend much time, but I have shown that where from these values have originated. And so, therefore, we understand that this is the value which is heat of formation of carbon monoxide minus heat of formation of carbon dioxide, which has originated from our original derivation, and this is 169,000 is basically 2 times heat of formation of carbon monoxide at 1200 degrees centigrade minus the heat of formation of carbon dioxide. Now, if we manipulate this term, because we have gotten it in a standard form. So, we will add 1.06 and we will subtract 1.06 and then we will make this. And then what happens is you also can see that this term has become a dimension of 1.3, which is O by C ratio. NaC is what? NaC is C by Fe ratio, okay, per moles of carbon per mole of carbon, moles of carbon, moles of oxygen per mole of carbon. So, the moment you multiply these two terms, the resultant terms becomes a dimension of O by Fe. Okay. So, all here terms are given in terms of O by Fe. So, this is also O by Fe, this is also O by Fe, this term will also come out to be O by Fe, because it is kilojoules per, kilojoules per mole, and this is also kilojoules per mole. So, the moment you invert, it is going to be mole by mole. So, the units are going to be all homogeneous, and the unit of this is 1.06. So, it has I have added this term because this term has significance, particularly in the bottom segment, that we have an O by Fe ratio, in only where O by Fe ratio known is in the metal, which is of course 0, okay, there is no oxygen, and the input feed, which is 1.06. So, I have added and subtracted. Now, this gives me, since the terminologies are, okay, there are terms here. So, this is O by C has a dimension of O by C, it is understood that this term will also have a dimension of O by C. If this, similarly, if this term has a dimension of O by Fe, therefore, you can check that this term will also have a dimension of O by Fe. So, all the O by Fe terms are here, and the moment you multiply this term with NaC, then this also becomes an O by C. So, dimensionally the equation is constant. What does this indicates? That we will look at it like y2 minus y1 is equal to NaC, which is m, okay, into x2, and this is x1. So, I have the appearance of 1.3 during the stage of derivation and the subsequent addition of 1.06, and that the equation, the left hand side of the equation essentially represents O by Fe, and the bracketed term in the right hand side in the equation represents the ratio of O by C. Therefore, it allows you to, for a given blast furnace operation, okay, where I will see that there is going to be fixed NaC, it allows us to superimpose this data points onto this particular line itself, and we will see that if we try to interpret it in terms of the diagram that I have shown on the right hand corner of the board. So, therefore, I will say this will pass through a point x1 y1 and x2 y2, where the points are basically, I would say, 169,000 divided by 282,000 plus EB, comma, and this is going to be equal to 1.06 minus dWRZ plus 1.06 EB divided by 282,000. And that is going to be equal to my what? x1 y1. And x2 y2 is the familiar point, that is the W point, and that is going to be equal to 1.3 comma 1.06. Therefore, it is at once clear that this point x1 y1, because this equation represents a straight line on a plot between O by Fe and O by C, and that this particular equation exhibits a slope of NaC passing through the same common point. So, therefore, we will conclude that the straight line which we have drawn on the basis of these two equations must now pass through another point which has the coordinate of x1 and y1, and this coordinate is termed as the h coordinate. So, therefore, it is one and the same straight line that we are talking about. So, therefore, the combined enthalpy balance, bottom segment enthalpy balance and oxygen balance equation tells us that a plot constructed for to show the variation of O by Fe with O by C will essentially indicate that the straight line thus constructed will pass through two different characteristics points. One is the W point, the other is the H point. The W point and the H point, as I have indicated, and I have mentioned several times, this factor 1.06, this dWz, they will depend from practice. This is the expression for idealized blast furnace operation when Fe2O3 is the feed and we do not have any impurities present, and it is a very simplified scenario. So, the coefficient of Eb 1.06 will change the moment you change the feed. Okay? So, therefore, O by Fe, for example, you have used, and you have a blast furnace where you are charging in, for example, some metallic Fe also into the blast furnace itself. So, in that particular case, O by Fe ratio in the ore material is going to change. Similarly, if the ore contains silica, MnO, P2O5, etc., 1.06. So, for all blast furnaces, do not use this particular prescription. Try to calculate that what is that 1.06 applicable for your scenario. What is that applicable dWRZ? Do not put 330,000 and try to draw a graph for every blast furnace itself. For every blast furnace, the factor 1.06 is going to be different. For every blast furnace, dWRZ is going to be different. So, therefore, I could say that the single, it is this line that with 1.06 and dWRZ is equal to 330,000 kilojoules per mole represents the straight line for an ideal blast furnace operation, as I have discussed in this particular class. For every other scenario, for every single blast furnace, you will have nevertheless such a line, but not necessarily passing through the point 1.3 and 1.06, not necessarily passing through x1 and y1 as indicated by this particular expression. That needs to be borne into mind without any ambiguity itself. So, therefore, it essentially indicates that other way I can put it, if I can on an O by C plot, an O by C versus O by Fe plot, if I can somehow calculate the dWRZ, if I can somehow calculate the coefficients of Eb, which essentially indicates that the oxygen input per unit mole of Fe produced via the ore material itself, if this coefficient can be exactly calculated, if dWRZ can be exactly calculated, then x1, y1 can be calculated. Okay? Similarly, if we assume for the time being that x2, y2 is also known and it is 1.3 and 1.3 and whatever you have calculated, because 1.3 is a thermodynamically considered one. So, we can take it to be correct or not changing. On the other hand, if you have calculated the 1.06 correctly, then we can also say that we know the x2, y2 points. Alternatively, if for a given blast furnace the coordinates of the point x1, y1 and x2, y2 are known, then what happens is we can mark this point on this plot, we can mark this point on this plot, and then what we can do, we can draw the straight line between these 2 points and extrapolate the straight line, and the extrapolation will give me the blast rate, and the extrapolation will give me here on the abscissa the O by C gas ratio. And of course, there is no need to say again that the slope of the line thus generated or thus drawn between the point H and W will give me a measure of the coke rate, and the slope is, as you know, is nothing but NaC, as I have discussed. So, this diagram, having known the coordinate of H and Ustaite point W and H, you can draw the operating line of a blast furnace. This is called an operating line of a blast furnace, and if you change any parameter, this operating line is going to change. Suppose today I am using one variety of ore, tomorrow I use another variety of ore. So, the line is going to be now changed because these coefficients 1.06 dWRZ are going to change with ore to ore practice. So, for a given blast furnace operation, for a fixed practice, we will have a characteristics H point, we will have a characteristics W point, and the line thus established will be called the blast furnace operating line. And this diagram in the statistics book is popularly known in the iron making literature as the Rixed diagram. So, graphically also, without solving going into the three equations that I have written here, without doing mathematical manipulations, without substituting the values, we can do it analytically, of course. If you can calculate dWRZ, if you can calculate the coefficient 1.06, that what is the appropriate value, three equations, three unknowns, we can calculate the values. There is absolutely no problem. That is called the analytical solution. On the other hand, for visualization of the results, we can also graphically represent, and the graphical representation of the blast furnace or calculations would start from calculating the coordinate of the point H, calculate the coordinate of the point W, then joining the line and extrapolating the line to get the value of the NOB and O by C gas. So, the values that we can determine analytically can also be determined by drawing the operating line, extending it to in either directions, and finding out the value of blast rate O by C from the intercepts, and as well as the Koch rate from the slope of the straight line itself. So, we will conclude the discussion here, and now I will try to rationalize that what we are trying to aim at as far as this operating straight line, what it can give us, the kind of information that it can give us, and what is desirable and what kind of an information it gives us, that we will try to now look at. So, let me draw this once more, and this is, suppose it is 1.5, and then this is 1, and this is 2, and we all know that O by C ratio will lie between, this is O by Fe, and this is, so 1.5, so this is 0.5, this is 1, so this is about W point, and this is the way we have calculated, suppose, yes, the blast point. This is the H point. So, we have drawn this line. Now, we have extended this line to get the value of the, I think I should improve on the drawing a little bit, so that you know that it is an extension. So, this is, yeah, that is better little, and then we have extended it. I am still at idealized blast furnace operation. So, that is why I have taken it to be 1.5. So, this gives me the top gas composition O by C gas, and this gives me the blast. And the slope is NSE. I have said during the course of discussion over the last few days or few lectures that higher is the content of carbon dioxide in the top gas, it essentially implies that we have an efficient blast furnace at hand. So, what we are looking at, that in the exit gas, the intercept here should move as far as possible close to the value of 2, and that 2 essentially represents, it is full carbon dioxide and it is full carbon monoxide, the other end or the converse. Okay? So, we would like this point to go in this particular direction. We would also, as I said, that the Koch rate of the furnace, efficient furnace will show us an relatively small Koch rate. So, higher is the Koch rate, less efficient is the blast furnace. So, therefore, we would like this line, operating line, to have, it is understood, the lesser is the stiffness of the operating line, more efficient is the blast furnace, because if you make it less stiffer, then what happens is you are going towards more carbon dioxide, and if you make it less stiffer, you are going to a decreased Koch rate itself. So, therefore, we would understand, we would like this point H, all our effort should concern that this point H should be moving in this direction. If the H point moves in this direction, then you are going to get more steeper line. Okay? So, that is not this is the target line. This is my target direction in which the engineering of blast furnace must move the H point. If it moves up, this is fine. If it moves this way, this is fine if it moves. So there's a, within this, it can move left, it can move up, it can move sideways also. There are three possibilities. Similarly, I would say that this line should not move in this way. That will make it more steeper. So this W point should try to move in this way, okay? Or the W point should, move a little bit, not upward, but little bit downward. That's going to, or this, if this has a direction of this movement, is fine enough. That's the possible directions in which we would like W and H points will move. The moment, if you ensure that the H point moves in these three plausible directions, or the W points can be made to move in these directions, we are going to generate in turn, in brief I can say, a less steep line, essentially meaning that we will have less coke rate, more carbon dioxide in the top gas mixture, and therefore smaller blast rate. You remember that what is the definition of productivity I have introduced. In the context of productivity, I have introduced a term and I have justified it. The total volume of blast, supplied in a day divided by the total, the blast rate per ton of hot metal. Nitrogen, we could have said that instead of blast we could have said oxygen, because nitrogen is inert in this particular case, but that's the way it is. Or we could just say total volume of gas supplied and total volume of gas used per ton of hot metal, but we know that it is oxygen which is used and not nitrogen per se. So therefore, I have also indicated, let me quickly revise your memory. So revisit this issue that we have discussed earlier, that the blast rate, if the rate of production, which is tons per day, TPD, can be increased by decreasing the blast rate. It is obvious, because the total volume of the blast supplied, we somehow get to a maximum value beyond which we don't wish to operate, because we have blast furnace problems like electrician, fluidization, flooding, etc. So therefore, having said that we have used maximum amount of this is sort of a fixed. So therefore, our effort to increase the rate of production, which is directly related with productivity, culminates in the reduction of the blast rate per ton of hot metal. So therefore, we are trying to move the NOV value in this particular direction. That is the desirable direction. So as you can now see, that any effort to let the point H move in this direction or let the point W move in this direction will have the consequence that we have this point NOB is going to be moving in the upward direction, and the moment we translate this in our expression. So it's a consistent discussion. The moment we translate this or visualize this with regard to our definition of productivity, we will say this whole exercise will culminate in an enhanced blast furnace production. Okay? Now let us see under what condition the point H can be moved upward. Now, as you have seen that this is the point x1 and y1, okay? So we can move the point. For example, this point is not going to be too much sensitive with regard to the enthalpy of the blast, but if you can see, if you increase the enthalpy of the blast, this point is going to be, x1 is going to be decreased. So x1 is this direction, so the point will be moving in this particular direction. So a higher enthalpy of the blast, as far as the expression for the x coordinate is shown, is going to be related with what you call a higher enthalpy will cause this x1 to move in this particular direction, so towards the ordinate itself, and as a result of which this is going to now give us lesser amount, because we have supplied some part of the heat through the blast. so the coke rate will decrease. Okay? So the line is now going to occupy something like this. This is going to be the revised line. If that's what happens, if you have an enthalpy of the blast, so we can say that the line is going to be, this point will come suppose here, the new location as per this discussion. Okay? So now the line is going to be something like this, is going to continue to pass through this, and as you can see here, that is going to be the line. The moment you have made supplied more enthalpy through the blast, then what happens is now the coke rate of the furnace has become this, the coke rate of the furnace is decreased because the line has become less, and then you have the total amount of blast which is required is also decreased, and as a result of which, if you translate to this particular expression, you will see that the productivity has increased. So one way, so therefore it is desirable to use as high a temperature of the blast as possible. Okay? And but of course there are limitations as far as the equipments are concerned. We have it's a heat exchanger. If you remember, the metallic blast heaters, as I have introduced used for smaller furnaces, are not as efficient. On the other hand, the stoves that we use really require to be enormous height, because the residence time of the gas is going to be important. It's a heat exchanger, and when it is on gas, the stove is heated up. When it is on blast, the stove gives up its heat to the blast furnace, to the blast, and therefore this transport of heat, which depends on the residence time, which depends on the surface area, there are certain constructional problems that we cannot really go beyond 1200-1300 degrees centigrade through the standard stove that we use and the kind of bricks that we apply, okay, in those stoves. So there is a limitation of the equipment, but theoretically speaking, I would say higher is the blast temperature, more efficient is the blast furnace operation. We would like to say that dWRZ, if you look at this particular point, this term is not sensitive to dWRZ, okay, but the moment dWRZ is going to be smaller, we can understand that this term, which is a negative term, then what happens is this term is going to be now much, the numerator has become smaller, so as a result of which this has become smaller, and therefore the negative value, this point is going to move in this particular direction. So if you have a smaller dWRZ, this point is going to move, this term is going to be unaffected, x1 coordinate is going to be unaffected, but the y1 coordinate is going to be less negative, so the dWRZ point is going to move in this. So this point is my higher enthalpy point, high enthalpy of the blast, and this point is my low dWRZ. And if this is the case, then we can see that we will have still the combined effect. Okay. So this remains the constant point, assuming that it passes through 1.3 and 1.0, but if dWRZ is now smaller, in that case what happens is we get. And what makes dWRZ a smaller value? That means if dWRZ, we have seen that it contains, there are three basic components for an idealized case. Okay? I repeat again, it is supply of the heat to break the bond between oxygen and iron in those tight structure or molecule. Okay? Now you have, second step is, once you have released iron at 1200 degree, you have to take that iron to 1800 degrees centigrade or the melting temperature. So that is another enthalpy, so you supply that heat. And then the third is that you have to dissolve 4.3 weight percentage carbon into that liquid, that is the third component. This is the bare minimum three components of the demand term itself. Now for example, you have surface losses through the bottom segment, that could be another term. You could have metalloid reduction, you could have slag formation, you could have lime heating up. You have to supply the calcination heat, and there are so many terms which can get added up to the demand terms itself. Okay? So the demand term essentially will include, in the case of a practical blast furnace, many additional terms in addition to those three which I have shown or told repeatedly in this or the earlier lectures. So, the moment you reduce dWRZ, so the point will move in this way, or on the other hand, conversely I would say the moment you increase dWRZ, the point will move in this particular, this is the increased dWRZ. So, we will have now, you can see the consequence of dWRZ is this, that is the dWRZ. So, now you have a much larger blast rate actually, which may not be visible to you here, and this is higher dWRZ. Therefore, we can understand that suppose, as I have indicated, small furnace versus a bigger furnace, okay, producing. So, if you have 4 furnaces of 750 meter cube as opposed to 1 furnace of 3000 meter cube, in that case you will see, though one of those smaller blast furnaces will correspond to this steeper line, on the other hand larger blast furnace is going to correspond to a less steeper line, because the simple fact that you have less heat loss from a bigger furnace owing to smaller surface area to volume ratio. If you have, for example, lot of gangue materials, okay, then you have the slag volume increases, so more heat supply is to be there, so the dWRZ is going to be increased, okay, and therefore the line will tend to move, become more steeper. So, a bigger blast furnace, relatively pre-processed ore which does not contain much impurities, a good quality coke for example, okay, these are prerequisites for moving this point H in a positive direction. So, I have said enough about that, what will drive this point in an unfavorable location and what will drive this point in a favorable location, and as I have indicated, the higher blast temperature and a low dWRZ is actually required in order to improve the blast furnace operation, and this we can visualize immediately in terms of our expression of productivity, that these two cases will lead to a reduction in the blast rate, and as a result of which manifest in increase in the production. What about the point W? 1.06 of course, as I have indicated, will depend on the ore. Okay? For example, if you have silica reduction, if you have manganese reduction, your phosphorus reduction, that 1.02 could become 1.16, 1.17, 1.18 and so on and so forth. So, the impurity present in the ore will affect this, and therefore, as a result of which what happens is this point will try to move in a, if you assume that 1.3 remains constant, so this point will try to move. Actual cases, for an ideal case it is 1.06 here, but for an actual case this point is going to move, okay, and as a result if it moves, then what happens is the line becomes more steeper. So, higher is the value of 1.06, okay. In that case more steeper is going to be the line, and as a result of which the blast furnace is going to be less efficient, and then if the point moves here, and you can see that the line will become now substantially more steeper than the original line that we have indicated here, okay. But what we want to do? We want to that is the one. So, I would say I can draw this line. So, this line I am drawing, the enthalpy remains fixed, and now we have more impurity in the ore, and as a result of which more impurity means the 1.06 factor now becomes 1.17. Say with silica reduction, manganese reduction, phosphorus reduction and so on, just metalloid reductions, only this point from 1.06 has become 1.07 and the line has become more steeper. So, therefore, and how does this point 1.06 could be smaller? It could be smaller because if you incorporate the metallic charges into the blast furnace itself. Okay? For example, relative to oxygen, if you have more metal charge, for example, if I can charge into the blast furnace the scrap of steel. I can charge into the blast furnace. Of course, internally this may get oxidized, but the moment I introduce the feed as Fe, then what happens is I assume that Fe does not undergo oxidation and it enters the elucidated reduction zone as Fe, which of course is debatable. But suppose if you increase the proportion of Fe, in that case W point can go downwards, because that 1.06 will be less with metallic charges incorporated into the blast furnace burden material. On the other hand, this 1.3 is also not sacrosanct. This 1.3 value, if you remember, was derived on the basis of an assumed thermal and chemical reserve zone temperature of 1200 Kelvin. But that 1200 Kelvin also can be maneuvered to certain extent and can be reduced depending on the reactivity of the coke and so on and so forth. So, the high temperature, high pressure, by maneuvering the pressure, by maneuvering the reactivity of the coke, this reserve zone temperature can be affected, and therefore, the reserve zone temperature can be moved in a favorable direction. So, if the reserve zone temperature moves in a favorable direction, in that case what happens is the value of 1/3 will become a little bit of higher, because carbon monoxide concentration is going to be decreased, and as a result of which the point is going to be. But as I said, it is much more easier. This point will not be affected to a drastic extent. Okay? Little bit this way or that way, this point W can be changed depending on the actual blast furnace practice. On the other hand, this point H can be significantly changed by controlling the blast temperature as well as the dWRZ, and as a result of which what happens is that by maneuvering this, the movement of this point in favorable direction, that is towards the left or in the vertical direction, a vertically upward direction, we can get into a favorable regime of blast furnace operation, because that is going to ensure a lower blast rate, and according to our definition of productivity, that a lower blast rate per ton of hot metal, because this NOB is also per mole of Fe, which essentially is a reflection of per ton of hot metal, we will say that we will have an increased productivity. So, I think I have given enough for the last 5 hours or so in the 5 lectures, the derivation of the equation, etc., and have shown that how one can do a heat and material balance and arrive at the blast furnace operating line diagram and draw meaningful conclusions which are consistent with the theory which we learn, or the things we introduce into the subject, and whatever we have, modern day blast furnace practices which I have discussed, for example, oxygen enrichment. I mean, you can visualize, the role of oxygen enrichment into this particular case itself, with regard to, for example, if you have oxygen enrichment, actually you will have lesser volume of nitrogen going out and more volume of carbon monoxide and carbon dioxide. So, the dWRZ term is going to be also. And if you remember, you have enthalpy of the blast. Okay? The enthalpy of the blast term contains what? It contains 0.79 by 0.21 factor. So, if you have 2% oxygen enrichment, so it is going to be now 77/23. Okay? That is going to be the ratio of nitrogen to oxygen, as a result of which the enthalpy of the blast is going to be changed, and as a result of which, once the enthalpy of the blast is going to be changed, you will have, it becomes more with oxygen enrichment, and then what happens is this point will try to move in the left direction. So, an oxygen enrichment increases the blast furnace productivity, that we have made a qualitative statement, but in terms of the equations that we have established also we can visualize. So, all the modern operating practices of blast furnaces can be very conveniently, quantitatively explained on the basis of the risk diagram, and I leave, up to you to explore those, when you have high height of pressure, which are the terms which are going to be affected in the equation, and how the points are going to be changing directions, and so on and so forth, when you go back and take this knowledge, to your hostel room. So, we will conclude our discussion of blast furnace iron making, and I think this time has come to move on, and the next 3 lectures I will devote very briefly. Today was the 13th lecture, and 3 more lectures if I take on alternative iron making and pretreatment, that will be pretty much the iron making content of the course, and then we will move on, I think, after the 3 lectures onto the new topic, or the subsequent refining of hot metal, which we call as steel making. So we'll stop here, and I'll meet you again tomorrow.